Now we're going to look at a more efficient implementation of the trapezoidal rule. This is called the recursive trapezoidal rule. This table indicates an integral approximation using this composite trapezoidal rule we talked about before, using a specific number of panels or subintervals. So we're going to let I sub k be the implementation of the composite trapezoid rule using 2 to the k to the minus 1 power panels. So, for example, if I is equal to 1, then we're looking at 2 panels. If k was equal to 2, of course, we're looking at 4 panels, and so forth, sort of a doubling the number of panels. And so that's what we're indicating. If k is incremented by 1, then the number of panels is doubled. We're going to let capital H represent the length of the subinterval, so the overall length of the interval that we're integrating from f of x dx. So what we've indicated here is this is if you only had one panel, so one subinterval, that's our regular trapezoidal rule. Remember the half the base plus multiplied by the sum of the two heights of the trapezoid. But what this indicates is if you were to double the number of panels so that you went from one subinterval, and then broke it into half, and then you continued halving so that you got finer and finer representations for the integral, breaking into pieces. What this indicates is how you can reuse the information you had from the previous implementation. So, for example, if you were to do only one panel, indicated here, if you needed to move on to I sub 2, which would be using 2 panels, this would tell you that all you need to do, is indicated here through this derivation, is take what you had from the first implementation with one panel and then just evaluate the function one more time. Again, keep in mind h is equal to b minus a. So you would evaluate the function at a plus h over 2, multiply it times h over 2, and that'll give you a new integral approximation. So this is kind of very nice because it reuses the data that you had before. You don't want to iterate all over again, because the points are equally spaced. So for example, in this case right here, for I sub 3, that would correspond to looking at 2 to the 3 minus 1, which would be 4 panels. So again, we doubled it from the previous one. So what you would do is you would take the result from just using 2 panels, which is indicated here by I2, take half of that value, and then add the result of h over 4 times these new functional evaluations. So when you move from I1 to I2, you have to evaluate the function one time. When you move from 2 to 3, you have to evaluate it 2 times, and so forth. So you're going to be doubling the number of functional evaluations each time. And this sort of is a general representation of how you move to the next number of the next doubling of panels with this general formula here. So what you would use is how do you go from ik minus 1 to ik? Here's the formula you would do. Okay. So very nice implementation of how to do trapezoidal rule where you want to keep doubling the number of panels. The general form, again, is indicated this way, that if you want to half the step size that you're currently working with, let's just say call it 2h, so half of it would be h. You need to take half of what you had before and then add, h times a summation of new functional evaluations. So that's just sort of a generic formula. And of course, you can then monitor the convergence by comparing the differences that you get between ik minus 1 and ik. As you keep doubling the number of panels, at some point you're probably going to get, you're going to exhaust the ability to get any more, a better and better approximation integral. So at some point you can probably just say, well, there's not much difference between ik minus 1 and ik, and I'll stop. If we go to the book, on page 203, there's an actual implementation of the trapezoidal rule, as I'm showing you right here. This is a function that, again, computes an approximation to integral from a to b f of x dx. calling the trapezoidal rule with k equal 1, 2 until the desired position is obtained. So what happens here is you get the module actually has an implementation of this recursive trapezoidal rule, where the new approximation is based on calling it with the function, the intervals, the limits of integration a and b, and what your previous approximation was, and then k, the number of panels. So again, I new is the same integral computed with 2 to the k panels, and this is just an implementation of the formula we had on the previous slide. Again, where you can see that we're updating right here, I new equals I0 plus h times the sum divided by 2. So very nice implementation of this way of approximating integrals using the trapezoidal rule with finer and finer meshes. So if we go back now to continue on our Newton-Cotes rule, where, and keep in mind, trapezoidal rule was just using a linear interpolant. Now we're moving up to the case where we're willing to use a quadratic interpolant. But of course it takes 3 data points to do that. This is called Simpson's rule. So illustration here is if we let h be the successive differences between our nodes, between say x0, x1, and then from x to x2, that'll be distance h, on the interval AB. Now what we're looking at is fitting a quadratic, where before with the trapezoid we were doing just 2 points, the end A and then the endpoints A and B. So now we need this midpoint. And that's exactly what the formula suggests that you do, that to approximate this integral, you'll take the function evaluation at f of A plus 4 times the function evaluation at f of A, the midpoint, plus the evaluation of the function at the end at B, and then multiply that times h divided by 3. Okay, so this is using a parabola rather than a straight line. And for the composite rule, you'll do the same thing that we did with the composite trapezoid. You're just going to break it up and then use these midpoints in each subinterval so that you can construct your quadratic. And so basically on every of the adjacent panels, that's what you're doing. You're using 3 data points. Again, you have to look at xi, and then you have to look at xi plus 2, and then you have to use xi plus 1. So it takes 3 nodes now instead of 2 to approximate the area under this quadratic, or this parabola. So this is called Simpson's rule. And so again, you can now think about using higher order polynomials if you want on the subinterval and integrate under them as well. So that's the general approach in Newton-Cotes. So this is what the composite Simpson's rule looks like. You will just break the interval up into subintervals. AB goes from x1 to xn, and then you're going to integrate each one of those you're going to integrate on each individual subinterval, and if you do the algebra, this is generally what the integral approximation looks like. So you'll have the 2 endpoints, x0 and xn, and then different coefficients on the different interior points, and all that'll be multiplied times h divided by 3. So again, composite Simpson's rule works just the same way with composite trapezoid. It's just that it takes 3 points on each subinterval to approximate the function, to get the function value, versus just 2 with the trapezoidal rule. So just like we had Richard extrapolation as an approach to improve upon the approximations of derivatives using finite difference approximations, you can do a technique called Romberg integration. This is section 4 of chapter 6. And it's a combination of using the trapezoidal rule with Richardson extrapolation so that you could try to get a little bit more accurate approximation using repeated implementations of trapezoidal rule. So let's say, for example, that, and you'll see a little bit why we index it, let's let Ri, 1 equal I1, where I1 is an approximation to, say, an interval, a definite interval that you've done, and let's say you've used the trapezoidal rule with 2 to the k minus 1 panels. Okay, and the error, the term, and using trapezoidal, we know this. We've seen that the leading power of h is h squared. So that would be the error in achieved by using this integral approximation I1, where h is b minus a divided by 2 to the I minus 1 panels, or the panel. So the overall h is the panel width. So, so suppose we've done the integral approximation with one panel, and then we'll call that R11, and then suppose we do it again with two panels. And again, we've indicated with the recursive trapezoidal rule how we could easily get I2 from I1. So let's suppose we've done both. We've approximated the integral using one panel, and then we approximated it using two panels. Okay. So having those two approximations, then what we'll do is we'll compute a new estimate called R sub 2, 2, and do Richard extrapolation to try to remove that error term. Remember, the leading error term in terms of the power of h is always some constant times h squared. So again, the error in doing our two approximations for R11 was over h squared. For doing R21 was O of h squared. And this looks very familiar to you. This is just doing Richard extrapolation like we did before, finite differences. And when we do that and just clean up the algebra here, the R22 value would be 4/3 times what you get when you integrate with two panels minus 1/3 what you get when you integrate with one panel. And what's nice about doing the extrapolation is the error term now in this particular approximation is order h to the fourth. You've eliminated that O of h squared error term the same way we did it for finite differences. We're just using some subscripting here, which you'll see in a little bit why we do that. But this is just doing Richard extrapolation where each one of these terms here represents doing an integral approximation using, in this case, one panel and then using two panels. Okay. So you can see what the process is like. Just keep taking more and more panels, doubling each case. So for example, if we continue with 4 panels, and we'll call that R3, 1, which will be defined to be I sub 3 back in our table. That means it's going to use 4 panels. And then we'll repeat Richard extrapolation using the last two approximations. R31, again, is using 4 panels. R2, 1 is using 2 panels. So we're extrapolating now using successive number of panels. And we'll get a new, after we do the extrapolation, we will get this value R32. So in some sense, you can think of what we're generating as sort of an array of results. Okay? So we started with one panel here, then we went to 2 panels, then we did an extrapolation to get this value, then we used 4 panels, and we did an extrapolation to get this value. But everything in this column, this second column here, has its error as a leading term of h to the fourth. So we're getting more accuracy now as we move along. And the goal is to keep moving in this process until we're happy in terms of getting approximations with lower and lower error terms. In fact, again, we could do another extrapolation and produce this value called R33, and numerically this is what it would look like. So the error in R33 now is O of H6. So what's interesting now is all of these approximations, which don't involve extrapolation, those will order h squared. Remember, these extrapolations were O of h to the fourth, and then we're finally using these last two to eliminate the h4 term, and the next term in the error representation is O of h6. So if you continue this process, what you're doing is you're doubling the accuracy each time. Well, you're about a power of 2, I should say. So continuing the madness, you could go to R44, which would be extrapolating the last two approximations you have column-wise, and you'll again eliminate the O of h to the sixth term, and what's left is an O of h to the eighth term. So the error now is the error is order of h to the eighth. Should be an exponent there. So O of h to the eighth. You would keep iterating this way until successive diagonal elements are sufficiently small. So you're looking at these diagonals. This is the first panel. This was doing an extrapolation, and then all these are extrapolations, but you're looking to see when these are sufficiently, when the difference between them is small. In other words, you're converging on this diagonal to an element, to probably the best guess or the best estimate of what the integral is going to be. So you're just monitoring what those diagonal elements are as you do the integration. So the general extrapolation formula that could be programmed, which we'll show you the code for it, is very simple. This is the general formula for how you advance the extrapolation process from the initial case of using one panel. And we'll look at the code on page 209 to 210 called Romberg.py, and we'll look at an example 6.7 on page 211 and 212 when one is asked to approximate this particular function, integrating from 0 to the square root of pi. The idea here is that you always will have to define a function that's going to provide the integrand. So here's an illustration for this example of coding up the function, because you're going to have to pass the name of that function f, which will be executed this way, to this Python function called Romberg. It's very easy because it's just going to take that function, the limits of integration, return your integral approximation, and the number of extrapolation steps that it took to achieve some default accuracy. So let's look at this code that implements Romberg integration. Remember, this is just doing Richard's extrapolation with the composite, with the trapezoidal rule, and as indicated in the book. Again, we're on page 209. Let's go back to that. So we're on page 209. Scroll towards the bottom of the page. And you can see here's the module explanation. Again, it needs the name of the function, so you have to code up the integrand as a function f, or any name. You can call it anything, but you're going to have to pass it by name to this Python script. The limits of integration, and then it's got a default tolerance on, again, the difference between the extrapolations to see how it's converging is 10 to the minus 6, but you can make it bigger if you don't need that much accuracy, or you can make it a lot smaller if you need more accuracy. And again, it returns the integral and the number of panels used. So it's the number of, ultimately, I guess I was wrong. It was not the number of extrapolation steps, it's the number of panels that were used before it stopped. If we just scroll down a little bit more, you can see how the code looks like. It will use the trapezoidal rule, so you'll notice that. You'll see from trapezoid in point star. Here's the definition of the function. This is a function to do the Richardson extrapolation formula that was in the notes. So this is just coding up that formula that we just had in the notes. Here's the calling, doing some initialization, and then calling the trapezoid rule, and then implementing this series of taking doubling a number of panels, doing an extrapolation, and then just checking to see the difference between the new update versus what you previously had, and then just keep doing that. It looks like it's defaulted to 2 to the 20th power in terms of the looking at the number of panels. It's because it's returning 2 to the k minus 1 as the number of panels. So it's starting with 1 and it's going up through to 20, so it's 2 to the 20 minus 1, so 2 to the 19 power is the maximum number of panels it looks like it's going to use. And if it doesn't converge, if this absolute value of this error is not small enough, then it'll just print out a message it did not converge. So if we look at the example that I wanted to actually demonstrate for you, 6.7 on page 211, scroll down to the bottom again. This is just using what we just had on the screen for in the notes. We're looking at this function 2x squared cosine x squared dx, integrating from 0 to square root of pi. Again, you code up the function here, f, then you simply call the Romberg function. Notice that I'm using the square root function available from math library, square root of math.pi, and then just print the integrals, and the n would represent the number of panels, which would be the number of evaluations. So it'll turn out to be the number of functional evaluations it takes, and it is the number of panels, I guess, and so that that's an error represented in the book there. It's not the number of evaluations. It should be the number. This should have read the number of panels. So it's a typo in the book. So so let's actually run the code and see, and just look and maybe make some adjustments to some of the parameters and see the effect. So let's again look at this very simple illustration. Again, I'm not interested in you having to code up the Romberg integration formula. It's already available for you. So we're just looking at how to use it for this particular integral that we want to approximate. And again, I'm going to make a change here. That shouldn't be the number of evals. That should be the number of panels. So so we've changed that in the code to print panels rather than number of evaluations. And if we just simply run the code, making sure we type the name right, and you'll see that we get exactly what the book had, 64 panels. Let's keep in mind that the built-in accuracy for that Romberg function was 10 to the minus 6. If we needed higher accuracy, so for example, suppose we doubled it, or we actually halved it, so we wanted 6 more decimal digits, so we're going to make the error 1.e to the minus 12. Let's see how long it would take. It would actually use, it would usually 256 panels is what I'm saying. So rather than 64 panels, it would take 256 panels to get that kind of accuracy. Right? So we would pick up perhaps double number of digits in the accuracy to the integral. Likewise, if you were to make an adjustment and make it very small, in other words, you make it very large, so we're willing to have a rough approximation to the integral and then run it again. That only would take 16 panels. And again, the cost is lower. So there is no gain here without some price. If you need more accuracy, it's going to take many more panels. It's going to take more subdivision, or another person might say a finer mesh to get that kind of approximation to the integral that you need. So that does it for Romberg integration and our use of Newton-Cotes formulas to approximate integrals. In the next lesson, we'll be looking at a different approach called Gaussian quadrature. It's a different way of selecting the nodes and the corresponding weights, and you'll see what motivates that particular approach to approximate integrals in our next lesson.